Okay, so hopefully you did a little bit of work to determine that the mass drops out. For the car, let's instead look at a amusement park ride called the Turkish Twist. You'll see at the bottom of the slide a YouTube video in case you're not familiar with this particular ride. I believe it's up at Canopy Lake Park. The idea here is that a number of people are put up along the wall of a drum. There's a platform underneath them, and as the ride begins, the drum begins rotating in some direction. And when it speeds up fast enough, suddenly the floor drops out from under the rider, who predictably starts shrieking, and then eventually the floor comes back up, the ride slows down, everybody grins awkwardly, and if you're my children, you get a physics lecture or a quiz. But anyways, so if you're not familiar with it, you can see a video of it here. If you go to pick up the slides off Canvas, you can just click that directly. Otherwise, it's probably ghastly, a bit of typing. So the Turkish Twist ride up at Canopy is a 14-foot diameter drum. It turns at 9.5 meters per second. And there's a design assumption that the coefficient of sliding friction between your clothes and the wall of the thing is 0.4. A typical person is about 68 kilograms, that's 150 pounds, maybe a little light, maybe a little heavy, but call it an average. And the main thing we want to understand is, well, does this ride work for both me, who is over 150 pounds, and my kid, who's well under 150 pounds? The condition for the ride working is that the person does not fall downward when the floor drops out from underneath them. As we saw with the car, the car on the wall of death, the source of your failure to fall, that sounds really funny, is the friction force. And so your condition for not falling is that the friction force on your rider is equal to the gravitational force on your rider. Friction force is also equal to the coefficient of sliding friction times the normal force. And we found notice that we're going to use the centrifugal force way of thinking about this now. We found that the normal force in turn is equal to the centrifugal force. We could just as easily say that it's equal to the centripetal force. Those are equal in magnitude, opposite in direction, but the drawing becomes a little more neat when you think about it from a centrifugal force point of view. Once we've said this, we can set centrifugal force to that, mass times velocity squared over r. And that means that in turn, the friction force, and now I'm going to start drawing in here, the friction force is equal to coefficient of sliding friction times the mass times, that's an r, not a v, times r squared over the velocity. Sorry, that was a v. It's been a long morning already. Okay, so times velocity squared over r. And that we can set to, as we saw above, the gravitational force on the person, so mass times the acceleration due to gravity. Oh, look, this is getting to be kind of a theme here. The mass drops out of the equation. And we can find that the condition for having the person, the rider, not fall is that v squared over r is equal to g divided by the coefficient of sliding friction. And in fact, for any radius of the drum, r, then you can set your v squared according to this, and everything else becomes sort of engineering trade-offs. How tight you want that circle to be, how fast you want to spin people, what your insurance requirements are, sort of pragmatic considerations like that. Okay, so that's the amusement park ride application for all of this. From a more practical point of view, all right, maybe this is not very practical either. Space travel has a problem in that if you're out in space for too long, it causes bad physiological effects on the astronauts. The human body was kind of designed to be operating in the Earth's gravitational force, gravitational field, and as a result, when you are in other locations with less, or I suppose more, gravity, various functions of the body tend to deteriorate and work poorly. It's an active area of research. In fact, how often the human body needs to be exposed to approximately Earth gravity and how close to Earth gravity you need to get in order to make sure that the astronaut does not physically deteriorate over long stays in space. This has been considered by science fiction writers for a very long time. Here's, for instance, an image that is probably familiar to some of you as the space station in Kubrick's 2001: A Space Odyssey. And this design is one that, in theory, provides an opportunity to have artificial gravity. This here is the living space. The outer surface of this, the outer rim, if you can kind of get your head around this, would be the floor of a long continuous hallway. The space station rotates about its center axis, providing a centrifugal force, which, if the rotation speed is set correctly for the radius of your space station, in that case you have a centrifugal force that is holding your astronaut to the apparent floor of the working space hallway and providing him or her with at least the appearance of being in a gravitational field that's equal to Earth's gravity. One implication of this construction is that as you move towards the center of the space station, so if, for instance, you had some maintenance work or something that you needed to do up here, you maybe climb a ladder up this passage here, as you move in towards the hub, the radius r decreases, which means that centrifugal force decreases. And I want to kind of pause on that one for a moment. We said centrifugal force is equal to mv squared over r. So it seems that if r goes to 0, then centrifugal force should in fact go to infinity, and the gravitational force on you in the center should be much higher than the gravitational force on you out at the rim. The reason this is not true can be seen when you convert the linear velocity that we're talking about in this equation to an angular velocity. Omega, lowercase omega, as we'll see when we start talking about things rotating, is the angular velocity, the degrees per second that a spinning object traverses. So if you take a point on this object, follow it round, say 360 degrees, the angular velocity would be, 360 degrees per however long it took to go round like that. In this case, what we do is we can recognize that the centripetal acceleration is being equal to v squared, the linear velocity squared over the radius, is now also the angular velocity the angular velocity squared times the radius squared divided by the radius. when you do that, then the centripetal acceleration is equal to omega squared r. And now you can see that as r goes to 0, in fact, the centripetal acceleration and therefore the centripetal force, or centrifugal force if we're looking from that framework, goes to 0. So I just wanted to take a moment there to address that, because this idea that the gravitational force on you should decrease as you move towards the hub does not make a lot of sense just pulling that equation directly. You have to actually move into angular velocity in order to understand why this should be so. Be warned, people who are making movies about space. All right, I'm going to break my lecture here, get myself some more tea, and move on to rotating objects.